Hello, purpose of this video is to analyze quadratic functions written in standard form. When I say analyze quadratic functions, there's two parts of that I want to deal with. The first thing is, this of course being an equation with two variables has infinite solutions to it, and when we analyze, what we're looking for is where are all the solutions to this equation going to be laid out. So we can make predictions right off the bat, and then we can do further analysis to get a more accurate picture of where all the solutions exist. So the goal here is essentially the concept of analysis using algebra. And before we go any further, I want to define analysis as taking a complex idea and breaking it down into simpler parts. So let's start with some simple parts. When x equals 0, I see that the value -4 will be the solution 0, -4. And then I see that this linear term is going to cause the function to increase for a little while, but this quadratic term, being negative, is eventually going to pull the curve downward. In other words, I anticipate a sketch that looks something like this. Now, as to whether or not the function is going to cross the x-axis, I think not, because this is a relatively small number. It's not going to have enough force to push the solutions up over into the positive realm. But we'll know for sure when we do further analysis, beginning with finding the y-intercept. Again, that's relatively self-evident, but I make an acknowledgement that when x equals 0, y equals -4, the y-intercept is not necessarily the last number in a function. It is necessarily the value of the function when x equals 0. Continuing on, we have the axis of symmetry. The formula for the axis of symmetry is taking the opposite of the b value and dividing it by twice the a value. In this case, the a value is -1. Double that, we get 2 times -1, and the b value is +2. I take the opposite of +2, and that generates excuse me, x equals 1 as the axis of symmetry. That enables me to find the vertex. I simply evaluate the function when x equals 1, and I find that -3 is the outcome. And so 1, -3 is where the vertex is going to exist. I also have a point of symmetry. Essentially, if I know where my y-intercept is and an axis of symmetry, then across the other side there's going to be another point that has the same y value, and so instead of 0, -4, I go across the axis of symmetry and find 2, -4 as another free solution to this equation. So I start graphing the y-intercept, the vertex, the symmetry point, and that's not really enough to make a good parabola, so I also recognize that if I go over 2, down 4, I'll get 2 other points to make my parabola. I label all the important parts of the parabola, and then I can go on to Desmos. You can see here is the actual graphing calculator set of solutions to the given equation. You can say I represented them fairly well according to this picture. Now, clearly you can see from the picture that there are no x-intercepts. But what I was wondering is, what happens if we do try to find the x-intercepts using algebra? Now, for starters, I notice here that, first of all, because I know the vertex is 1, -3, I can rewrite the quadratic function from standard form into vertex form. This will enable me to use algebra and inverses to find x-intercepts if they do exist. So I'm asking the question, are there x-intercepts? Once again, clearly from the picture we can see no, there are not, but my question is, how does the algebra say there are no real x-intercepts? We start with substitution. We're going to let y equals 0, because that's right here. This is when y equals 0, it's going to be x-intercept. So the question is, what value of x will make the value of this function equal to 0? Once again, from the graph I can see there is no real value for x, but again, what happens to with the algebra? So I add 3 to both sides, and then I get rid of the negative by multiplying both sides by -1, and then I take the square root of both sides, remembering absolute value, and that's where I see a problem. We have the square root of -3. So we need to explore that a little bit more. So, starting with the square root of -1. It turns out that the square root of -1 is called not a real number, and the problem is there is no number among the real number set that if I multiply by itself I end up with a negative result. However, this is a common occurrence, square roots of negative numbers in mathematics, and so mathematicians decided that they should define square root of -1 using a symbol. And so they chose that symbol to be I. I is now officially defined as the square root of -1. If you see the square root of negative 1, you can replace it with the letter I. If you see the letter I, you can replace it with the square root of negative 1. These are interchangeable as evidenced by that equal sign. So, just exploring some patterns here. 1 square rooted is 1. The square root of negative 1 is I. Square root of 4 is 2. Square root of negative 4, 2I. Square root of 9 is 3. Square root of negative 9, 3I. In our instance, the square root of 3 is the square root of 3. I can't really simplify any further, but the square root of negative 3 will be I times the square root of 3. So these are just basically two different ways of symbolically expressing the same truth. And so now you know what that looks like. We could express the truth, the square root of negative 3, as this imaginary number. So I break up the absolute value by considering both positive and negative alternatives, but you'll notice here, instead of negative square root of 3, I wrote I square root of 3 and I square root of 3 here. And I'm going to get rid of the negative sign on this one by multiplying both sides by negative 1. And in the end, I determined that the two solutions to the equation are x equals 1 plus or minus I squared root of 3. Now, there's this thing called real numbers, and real numbers are numbers that you know about. And these are called complex or imaginary numbers. These are numbers that are, well, a little bit more broadly defined than real numbers. But this number line where I plot numbers is a real number line. It does not have any non-real numbers on it. And this is the real number line for the y-axis. It has no non-real numbers on it. So I cannot plot these on my traditional real number plane. But we can say that there are some imaginary solutions to this equation up here. So there you have it. Enjoy.